welcome back to the fourth class of this week. Up till now, we have talked about mostly the enzymatic glucose sensors, which is following up on our previous week while talking about insulin as a murder weapon and insulin and the challenges in the diabetes. Two very contrasting situation, and this week we are talking about the basic of the glucose sensors. The reason to start off with the glucose sensor, just a brief recap, because in the world of biosensor, the first biosensor which was developed by Clark was about an oxygen sensor, and we will talk about that Clark electrode next week, the design of the electrode, and exactly that is where all the fabrication and configuration of the electrodes, reference electrode, working electrode, standard electrodes, all those things will come, the role of the anode, role of the cathode, the electrocatalytic reactions, and how really the whole system is transformed into a device. But this week, before we get into the nitty-gritty details of the electrochemical sensors and the electrochemistry, we are taking a case study of glucose sensor, because that being the very first sensor which has been developed over last 40, rather almost 60 years. So, if we look at the basic of the glucose sensor, as we said that it is basically in any analyte, any sample, say it is a urine sample, it is a blood sample, it is a soil sample, it is a plant sample, you want to detect glucose. So, there are tons of other molecules present there, and they can always interfere in the estimation of glucose. So, you have to have a selective way to isolate the glucose, maybe a membrane, what we talked in the last class about the polycarbonate membrane, which was developed initially in order to reduce the interfering species, which may delay the detection process, and followed by that glucose in the presence of oxygen, while there is an enzyme glucose oxidase, glucose is converted into gluconic acid and oxygen is reduced to peroxide, and there are multiple ways you can do the detection process. Just to summarize back on the slide. So, in an enzymatic reaction, this is the basic reaction we are talking about. Glucose in the presence of glucose oxidase is converted into gluconic acid, and the oxygen which is helping in this reaction is converted into peroxide. This peroxide is again could be oxidized back, and during this process, this is the kind of reaction which is happening, and you are quantifying it. Now, in terms of glucose sensing, one of the challenge is this glucose oxidase. We talk about this molecule glucose oxidase, it has a catalytic site which is very embedded inside the structure. So, if I call the catalytic site as this one, so then there is a glucose binding site, there is oxygen binding site, this is the glucose binding site, and here you have the electron transfer happening. So, one of the challenges what we discussed in the last class, in space, if we look at it, and especially in a 3-dimensional space, if the reaction is taking place so much deep inside the pocket, for an electrode sitting somewhere out here, it is a lot of loss of signal which will reach here. So, you need substantial amount of glucose to get converted. So, if your sample has lesser glucose, the sensitivity will be compromised. in order to circumvent that problem, there are a lot of development which happened. But before I get into the development, the very first sensor which was made was based on how much oxygen is getting converted, the consumption of oxygen measured with Clark's electrode, how much say peroxide is being produced, this is another way of quantifying it, or how much electrode is being released when peroxide is getting oxidized, releasing 2 proton and oxygen. So, basically there are multiple steps where this reaction could be monitored. So, one is most of the assays which we have talked so far is called enzymatic assays, and enzymatic assays comes with its set of issues as I am mentioning you in terms of the architecture of the enzyme itself. So, this site is called the FAD site, which we have already discussed. So, some of the advancement what we talked about is how we could make the electrode or couple this site with a linker to the electrode, or have an electrode almost in direct contact with it, or have a flexible electrode which could enter there like a wire, or we could have the whole enzyme wired together. So, these are some of the challenges in the enzymatic assay. Today, we will go a little further about the most recent development, because the Clark's electrode is the story of 1960s and 1970s, and today we have traveled all the way to 2024, 25. So, if you look at it, this is a journey of almost 55 to 60 years, 6 decades, and a simple molecule like glucose is still a challenge to be detected, and there is tremendous amount of work which are happening. So, today we will talk about some of the most recent work which has taken place in this area. So, to start off with this brief background. So, we are talking about enzymatic and non-enzymatic sensors. The various initiatives noted in the previous section have had considerable influence on the development of the third generation biosensors, which are based on direct electron transfer in the absence of any kind of redox mediator. Such biosensors are able to operate at low applied potentials, thereby greatly reducing interference effect. However, as mentioned earlier, part of the challenge with these systems arise from the molecular structure of the enzyme itself. Many attempts have been made to try to create a successful matrix for transfer of electron between the FAD and the electrode by integrating of conductive polymer. So, this conductive flexible molecular polymers and emerging nanomaterials such as carbon based nanomaterials, that carbon nanotube, graphene, carbon graphene quantum dots, metal nanoparticle like gold, silver, copper, dendrimers, and many more. So, these are the approaches which have been followed during last 25 years. So, let us talk about the nanomaterial revolution in glucose biosensing. So, one of the very first development which has happened is, so say for example, this is a case study which I will be talking to you. Here you have the FAD which has been coupled with gold. Okay. So, this is the electrical wiring of the glucose oxidase, where electrical contact of the glucose oxidase by reconstitution of ApoGOX, which is devoid of the site on FAD functionalized nanoparticle. So, you have the enzyme, this Apo enzyme. When we talk about Apo glucose oxidase, this is minus FAD, because FAD is sitting in this pocket. So, if you could remove the FAD and you have the enzyme without the active site is called the ApoFAD. The ApoGOX and the FAD is out. On FAD, functionalized gold nanoparticle links to an electrode surface by dithiol bridge. So, here you have the dithiol bridge, which is a sulfur bridge. Thiol group is present there. Then what you are doing is that in that process, your FAD is in direct contact with gold. So, the electrode is in direct contact with the FAD site. Then you get the cyclic voltammogram obtained by developed modified electrode in the presence of different glucose concentration. And we will talk a little bit more, not today, in the next week about the voltammogram, how these voltammograms are generated. And here what you see is the schematic image of the surface modification with a gold electrode based on self-assembled monolayer of aligned single walled carbon nanotube and their subsequent modification to allow direct electron transfer to glucose oxidase. So, here again you have a dithiol bridge out here. You could see the sulfur sitting out there. Here is the amines. So, these are the silanes which are present, some of the sulfur containing silane, and here you have the carbon sheets which are present there. These carbons are being connected out here to a dithiol linkage to FAD, and here you are getting a direct electron transfer. These are some of the most potential advancement which has happened. Next, what you see is the gold nanostructure and their use in hybrid glucose biosensors. Gold nanostructure alone or in combination with other nanomaterials have been extensively studied in order to develop excellent matrices for biomolecules and in particular those used for glucose oxidase immobilization. For instance, we will talk about the nanoporous gold electrode has attracted significant interest in the field. Why the nanoporous gold is so favored material? Because first of all, the gold electrodes have better conductivity. Apart from it, gold electrodes are extremely stable. There is hardly any leaching which is happening there. Lastly, when you talk about nanoporous gold, that means the structure is something like this. That means it has large surface area and porosity. So, there are interconnected channels and it is a pretty porous intricate structure. So, that means if you could conjugate, if you treat this as an electrode and if you could conjugate it with this at the site of electron transfer, then you will be able to pick up excessively high signals from these nanoporous gold. And now, we will talk about one of the work which was done by Wu in 2015. So, now see, we started in 1960, we traveled to 1984, then 1987, now we are entering 2015. So, this is the most, these are some of the recent work we are talking about. He reported a glucose biosensor based on porous gold enzyme combination. Briefly, in this work, NPG, which is nanoporous gold, was prepared by allowing 12 karat white gold leaves in concentrated HNO3, which is nitric acid. The resulting freshly made NPG was immediately transferred onto a clean glassy carbon electrode. So, you have a carbon electrode, on that you have a layer of porous gold, which is a NPG layer, which was immersed, transferred into a glassy carbon electrode surface and kept under vacuum. The NPG surface was later immersed into glucose oxidase solution for enzyme immobilization. So, now this whole thing on this you are immobilizing the glucose oxidase. So, this whole complex is GOX, NPG and GCE, which is glassy carbon electrode, nanoporous gold and glucose oxidase bioelectrode, shown a sensitivity of 12.1 microampere and a detection limit of 1.02 micromolar towards glucose detection. The success of this biosensor was attributed to the three-dimensional structure of the porous gold matrix. which provided a good interface between active site of the enzyme and the electrode. So, this is one of the very first successful work of reaching to the site of electron transfer. Then comes Riva's work. This is again 2015-2018 work. Their group demonstrated the use of globular gold nanoparticle as component of nanohybrid structure by applying a series of chemical modification to establish a highly efficient immobilization matrix for glucose oxidase. So, this whole idea is putting more and more glucose oxidase, immobilizing them on gold surface. For this purpose, gold nanoparticles were functionalized with 3-marcaptophenyl boronic acid. A clean glassy carbon electrode was drop casted with bamboo-like multi-volt carbon nanotube dispersion in polyethylene imine. Then the glassy carbon electrode, your multi-volt carbon nanotube, and you have the PEI electrode was treated with gold nanoparticle and 3-marcaptophenyl boronic acid, and the resulting hybrid surface was used for glucose oxidase demobilization. The biosensor exhibited a sensitivity of 28.6 milliampere and showed a reasonable level of stability and reproducibility, such that the sensitivity was measured to be some 86.1% for the original value for 14 days of storage. The goal of such work was to design a novel hybrid nanomaterial by integrating the inherent advantage of the chosen component, namely gold nanoparticle and carbon nanotube. Thus, the presence of boronic acid residues allowing the easy immobilization of enzyme, while multi-volt carbon nanotube and PEI dispersion provided the best platform for transduction of electrochemical response. So, you see, slowly the whole process is getting more and more complex and complex and complex, yet just for one thing. Now, think of how complex this can be. They are doing all these things, and currently all the works are happening. Previous slide where I started the journey is immobilize this one, and as I say, if this is the GOX and reaching to the site of its electron transfer. It is for that one purpose for last 40 years. So many developments are happening. So, when I was presenting, I thought I would bring you close, because this is the world of biosensors, where with every step you try to have far better sensitivity, and it is a long drawn process, and this is just for glucose. Think of all the bioterrorist agent we have talked about. I mean, for each one of them we need sensors, and that is why in the beginning of the class or the course I was telling you, there is tremendous amount of opportunity, provided you have a holistic idea about the whole field. So, we will follow up on this in the next class, where we will talk about a little bit more about the enzymatic sensors, and we will move on to the non-enzymatic sensors. Thank you.